Great. And let's see, hopefully, so today I want to finish this discussion, functions. We have been here for too long, because then we have the next section that's going to be about cardinality, and then after that we're going to have our next exam. Okay? So the next exam is going to cover the things that we have discussed, which is so sets, functions, and then cardinality of sets. Okay? Including infinite sets, which is what we're going to talk next time on Wednesday to start talking about it. And all the material for that is already available for you to watch, the videos and so on. Okay? And do your reading. Okay, so let's finish this idea of function, and then as I mentioned before, there are special type of functions. There are functions that work very nice. For example, the property that we were dealing with before fell with a one-to-one, with a function that's now one-to-one. Okay? But if the function was one-to-one, we couldn't construct a counterexample like the one that we did. Okay? And it will work nice. So let's do some examples with this. So of course, we need to begin with the definitions. Okay, so let's see. Since you must have seen this already, at least the work that I asked you to do for Friday, then let me just give you the three definitions at once: one-to-one, onto, and bijections. Okay, so in all of this setup, so let A and B be sets, and f from A to B a function. So when you have a function, there are particular properties that a function could enjoy, and then they deserve a special name. For example, one-to-one. One-to-one is the one that tells you that every time that you put different inputs, you are always guaranteed to obtain different outputs. Okay? That's a formal definition. So if x1 is different than x2, then f of x1 is going to be different than f of x2. Okay? Different inputs always guarantee different outputs. So, number one, this is the notion of one-to-one. Now, what's the fancy word for this? Injective. Injective, the same thing. Okay? So, f is injective if the following happens. If for all A1, for all A1 in A, and for all A2 in A, we have the following. If A1 is different than A2, then f of A1 has to be distinct than f of A2. So in words, basically, this is A because A is the domain, okay? So for any two inputs that you pick, that's what I'm saying here. For any two inputs, if they are different, then we guarantee that the outputs will be different. Okay, that's what one-to-one means. Of course, if the inputs are the same, the output will be the same, right? That's what a function means. That comes with the notion of function. If every input has only one output. So now a function could have this property that two different inputs give you the same output. Then if that happens, like we did before, then it's not one-to-one. Okay, to be one-to-one, you always guarantee that if the input changes, then the output changes. Okay, that's what one-to-one gives. So I'm gonna write it in words. So what we're basically saying here is the different inputs always give different outputs. That's what one-to-one means. Now, as you probably saw in the homework, in practice, this version of the definition is not too helpful. Like, if you want to argue or show or prove that a function is one-to-one, if you follow this definition, you will need to argue that if you start with different inputs, then you end up with different outputs. And sometimes, depending on the formula of the function, this could be a little bit troublesome, complicated to do. However, there is an equivalent form of this statement. Who can tell me, how can I write this in an equivalent way? And that's what you have been doing actually on the homework. And that's how the book actually defines one-to-one. Because it's just the equivalent version of this is easier to work with. If you have a formula, f of x equals something, and you want to argue that the function is one-to-one, it's easier to work with the equivalent form instead of this. Who can tell me how can we write this in an equivalent way? No, how, so let's see. This is just a way of saying for any two inputs, okay? So let's just keep it like that. This one right here, what type of statement is this? What type of statement is the last parenthesis? An implication. So how can you rewrite an implication in an equivalent way? Keeping the implication form. Keeping the implication form. Contrapositive. What's the contrapositive of this?
If the image of A1 is equal to the image of A2, then A1 is equal to A2.
Exactly. And that's what you have been working with in the homework. And if you read the book, that's what they do. Because that's easier to work with. In other words, if the outputs are the same, then what you have to show is that then that's because the inputs were the same to begin with. Okay? So an equivalent way of writing this, so equivalently, F is injective if for every A1, for every A2, in other words, for any two inputs, that's what I'm saying here, for any two inputs, okay? For any two inputs, we have that if f of A1 equals f of A2, then A1 must be equal to A2. That's the contrapositive of the statement above. And as you know, an implication is contrapositive, they mean the same, they are equivalent, okay? Now, this one here is the one that lends itself more easier to work with. If you have a formula, it's easier to just start by saying, okay, whatever this is equal to this one, and then you just solve. You use algebra, you start solving, and then hopefully everything cancels out, and then you end up by getting that A1 equals A2. Okay? So, again, when do you use the red, when do you use the blue? Well, it depends on the problem. If you try to use this one and you're getting stuck or something, maybe you may want to take a step back and then try the other one. Okay? But typically, if you're given a formula, then you should try this one, the blue approach. Okay? But they're both equivalent. They mean the same thing. So in words, what would this be in words? Same outputs imply the same input. Okay? So if any two outputs are the same, then that's because the inputs were the same to begin with. Okay? Then the inputs are the same. Okay? So for example, thinking about it that way, if we take a step back to what we were arguing before, so if you try to do, if you throw in an extra condition that the function is one-to-one, okay, in this proof, if you throw the extra condition that f is, here we're doing it for an arbitrary function x. If I now say that f is one-to-one, it would allow us to go from this arrow to this one. How? Because you will say, oh, this means that there exists an A1 in S, so that f of A1 equals B. Okay? Then this one here tells me there exists an A2 in T, so that f of A2 equals B. But now that implies that f of A1 equals f of A2, right? Because they both have the same output. If the function now we know is one-to-one, what can you deduce? Same output implies same input. So A1 would be equal to A2, so we call it A, and then this line makes sense, and we could work our way up in here. In other words, if we throw in the fact that f is one-to-one, then this proof will work backwards, and we're going to have our equality correspondence between the two sets. Okay? So what I'm saying is, in general, you can only write a subset symbol here, as we proved. But if I now say that f is one-to-one, you can write equality. Okay? That's basically. Okay. All right, so that's the notion of one-to-one. And then I guess, let me say here, example/homework for you to try. I just said it. I want you to try to write it yourself. I just said it out loud. So if you want, watch the video, listen to my words, and then write it yourself formally. But now prove that. So prove that if f is injective, then for for S and T subset of A, we do have the inequality. Okay. So if the function, if we now throw in the fact that the function is injective, we can guarantee equality. Remember that this subset is guaranteed all the time. You don't have to worry about this one. We already proved this. What you need to then work with is this other direction. That's the one that you have to focus on. Okay? And that is what you're going to need the injectivity property. So think about it. Again, I already told you all now how to do it. So just try to put it in words yourself in writing. Okay, any questions about the notion of being injective? No? Again, we'll do some examples. Let me just get all the definitions out of the way. So number 2, so we did one-to-one injective. Now there is a notion of onto. What's the fancy word? Surjective. So remember, one-to-one is just a name for those type of functions for which different inputs always have different outputs. Now, onto or surjective is a name for those type of functions in which the image of the entire function is equal to the codomain. In other words, actually every element in B has a preimage. Okay, we don't miss anybody. That's what onto means. So the function covers the entire codomain. So F is surjective. I'm not writing words because it's worth saying it. If its image equals codomain, which is B. Okay, so formally, what we want to say is that every element in B has a preimage. So that means for every little b that exists an A such that f of A equals B. Okay, so that's what it means to be surjective. Every element in the codomain can be written as f of something from the domain. Okay, so notice that if you think about it, what we're saying here is that the image of A equals B. That's what we're saying. Okay, the image of the function equals the codomain, because the image of the function coincides with the image of its domain. All right, questions? You have a question? All we're saying here is that every element in B has a preimage. That's what we're saying. Okay, we're not missing anybody in B. So if you think about the picture with the arrows, our arrows have to be covering the entire B. There cannot be any single dot in B left out. Okay, every dot in B has to have a preimage. That's all we're saying. And then bijection. What's a bijection? Well, a function could enjoy both properties. A function could be both surjective and injective. When this happens, we call them a bijection. Okay, that's a fancy word. The not so much fancy word is one-to-one correspondence. Okay, so number 3. So one-to-one correspondence. Don't just say one-to-one. One-to-one means something else. Okay, you need to throw in the word correspondence, saying that it goes back and forth. Okay, and I would tell you why this is the case, why we kind of use this naming as well. Again, the fancy word is bijective or bijection. Okay, so F is a bijection if it is both one-to-one, so if it is both injective and surjective. Okay, so in other words, if you want to argue that a function is a bijection, you need to write 2 proofs. Number 1, you need to prove that it's injective. Number 2, you need to prove that it's surjective. Okay. Questions? All right. So bijections. Let me just give you the whole thing, and then we start doing examples. I'm going to give you a theorem. The theorem that I'm about to write down is actually very hard to prove. You need to actually study a lot of logic and set theory to be able to prove the theorem that I'm about to write down. But nevertheless, it's good to know that such a theorem exists, okay? And it has to do with the fact of existence of bijections, okay? Next, in the next section, we'll talk about cardinality. This theorem will make a little bit more sense. Because in a sense, if a function is injective, what are you saying? In a sense, you could say that the set A is smaller, is less than or equal than the set B, if you think about the cardinalities. Why? Because, first of all, everybody in A has to go to B, right? And different inputs have to have different outputs. So at least you have to have a B for every single little A that you have, right? You cannot have two A's going to the same B, because that's not injective, okay? So the function is injective, you could say that the cardinality of A is less than or equal than the cardinality of B. And in fact, we do say that, okay? But it kind of makes sense. But now, if you have a function from B to A that's also injective, what does that mean? So if you have a function from A to B, so here, let's say you will tell me, so the conclusion, so theorem. So let A and B be two sets and assume that there are two injective functions. There are two injective functions. Let's call it f from A to B. And then let's say that somehow you can find another one. Let's call it g that goes from B to A. What do you think that will imply? So let's see. If there is an injective function from A to B, by the way, in math, when we want to, if you don't want to say the word injective, sometimes we write this. We do this little hook to say that that this is an injective, and for surjective, sometimes we write this. Like instead of just one arrow, we write like two tips of the arrow. Okay, and this is sometimes the symbol that we use for surjective, so I don't have to say the word surjective every single time. This is in case that you are reading. If you read another book, you may come across this symbol. This means an injective, an injection, and this means it's a surjection. Okay, but I'll be using the words. All right, so if we have an injective function from A to B, again, the idea is that any two different inputs have different outputs. So B, the elements in B, at least you have to have one element for every single A that you have in here. So you could say that the elements in A are less than or equal to the elements in B, right? The cardinality of A, you could say, is less than or equal to the cardinality of B. It kind of makes sense to say that. Okay? But now, if I say that there is an injective function from B to A, again, by the same logic, you could then say the cardinality of B is less than or equal to the cardinality of A. So if you think about numbers, okay, if you think about numbers for a second, what is this telling me? If you know that X is less than or equal than Y, and Y is less than or equal than X, what does that mean about X and Y? They have to be equal, right? So if you think about cardinality, you will say that the size of A and the size of B are the same. Now, the next section, you're going to learn that how do we make sense of the same size? The set of finite is easy, same cardinality. And the same as infinite, how do we define same size? Via a bijection. Two sets have the same size if there is a bijection between them. A one-to-one correspondence. Basically, that's what we call it also one-to-one correspondence. You can make pairs, one-to-one. A guy from A with a guy from B. And so on and so forth, and then you cover everybody. You understand this? So that's what we mean by having the same size. So if you have an injective function from A to B, and then another function from B to A that's also injective, that means that then there exists a bijection. Now, where you can find that bijection, that's a whole different story. Constructing an explicit bijection could be very hard in general, but you know it exists, okay? And that's a very important theorem. This is what we call an existence theorem. Sometimes in mathematics this happens. We have existence theorem, which is a theorem that tells you that something exists, but it doesn't necessarily tell you how to get it, okay? Whether you can get it or not, that's a whole different story, okay? But at least it's good to know whether something exists or not. All right, so in the homework, there's one question that deals with this, which is basically just saying this statement, and you can see the name of the theorem there, okay? So assume that there are two injective functions, f from A to B and g from B to A, then there is a bijection, I don't know, I'm gonna copy it, I'm going to call it psi from A to B. Okay, this is a Greek letter. Okay, so then there is a bijection from A to B, or you could say from B to A, doesn't really matter. Okay. All right. Questions about this statement? No questions? In fact, let's see. Let me do an example that's in the book, and I think there could be a homework problem on that as well. Let's argue that there is a bijection between the open interval 0, 1 and the closed interval from 0 to 1. Okay? So let's do our first example. So show, number 1, show or prove, let me say prove. It's the same thing. Oh, I think I wrote something here. I just say prove. Okay, so prove that there is a bijection between the open interval 0, 1 and the closed interval 0, 1. Now I want you to be very careful. For finite sets, having a bijection literally means having the same elements. Okay. Now for infinite set, it doesn't mean that. Notice here, certainly the set on the right has more elements than the set on the left. Yes? This guy is a proper subset because this one, the one on the left, does not include 0 and does not include 1. This one does. Okay? So this one is still bigger. But nevertheless, what we want to argue is that we can actually have a one-to-one correspondence between these elements. Okay? And you could do this two ways. You could just go ahead and construct a function somehow from one of these sets to the other one. That's a bijection. Okay? Give me a concrete formula. Typically, this is very hard. Okay? Or in a much easier way, we can take advantage of this theorem that we just wrote down here. All we have to do is come up with two functions, one from 0, 1 to the closed interval, and then another one from the closed interval to 0, 1, just to make sure that they are both 1 to 1. If we do that, then we know there exists a bijection. Okay? And that's way easier to do. Okay? So, solution. Here's what we're going to do. So, first, the strategy is that first we would show, so first we find a one-to-one function. So, we find a one-to-one function. Let's call it f from the open interval to the closed interval. Okay? And I mean, there are many functions that we can do here. We can just, if you want, we could do the identity function, or we could do the function that takes an element and multiplies it by 2 or divides it by 2, whatever you want. Okay? For example, let's take the easy one, the identity function. Okay? Takes an input x and the output is x. In other words, the function is f of x equal x. Make sure that it's well defined, meaning that for any input, it does produce an output in the set that's supposed to do. It does, right? The input here are numbers between 0 and 1. The output is the same number. So the output lives in here as well. You understand this? Do you agree that this is one-to-one? You know, different inputs certainly will have different outputs, right? So here we don't even need to do the contrapositive version. So f is one-to-one. F is injective. Since x1 different than x2 implies that f of x1 is certainly different than f of x2, right? Because it's an identity function. So f of x1 equals x1, f of x2 equals x2. So they are different because we started with different stuff. Okay? So it's clearly injective. All right. Now let's construct the other. So now we also find a one-to-one function. Let's call it g. But this time I want it to go from 0, 1, the closed interval to the open interval. Now be careful, you cannot use the same function that we used before, the identity function, just because that would take 0 and send it to 0, and that's not defined. There's no 0 in the codomain. You understand this? The output has to be a number strictly between 0 and 1. So what can we do here? For example, and we just have to make sure that, for example, 0 gets larger, a tiny bit larger, okay? But in such a way that 1 gets smaller. Because if 1 gets larger, then we are outside of this, okay? So for example, we could play the following game. We could divide by 2, let's say. So by dividing by 2, if I write the function x over 2, the range of this is reduced from 0 to a half. Immediately. Understand this? But now, that's not, I already fixed the problem with the 1, but I need to fix the problem with the 0. Because I don't want to have 0. So don't just push it. I don't know. You can add like 0.25. Something. So, we can work with the formula x over 2 plus 0.25 or 0.1, whatever you want, okay? Just something tiny. Notice that what this does is it takes an input, divides it by 2, and then add 0.1 to it. Why am I doing this 0.1? Because this will then give me 0 plus 0.1, so this will send 0 to 0.1. You understand this? Now, notice that here I'm saying, because what this does, this x over 2 is not the 0.1 per second. This x over 2 takes this interval and shrinks it in half. It takes it from 0 to 0.5, from 0 to 0.5. Does that make sense? Now, all I'm doing is translating this by 0.1. So I'm still within range. The image of this function is from 0.1 to 0.6. It's inside there. Yes? So that's a perfectly fine function. So, in more formal terms, that's g of x equals x over 2 plus 0.1. You can do plus 0.2, plus 0.3. Just, you cannot do plus 0.5. If you do plus 0.5, then you're going to set 1 to 1, and that's a problem. Okay? So you have to make sure that you do plus something that's less than 0.5. Just pick your favorite number less than 0.5, and you can put it in. Now, we just need to argue that this is 1 to 1. Okay? So, claim G is injective. Now here, to prove that it's injective, it's easier to just use the contrapositive version. In other words, take 2 inputs and assume that they have the same output, and then argue that the inputs are the same. Okay? So let x1, x2, let me use A's and B's. So let A and B be 2 elements between, in the closed interval, 0, 1, such that, we have 2 inputs such that they produce the same output. What is our job? What do we need to argue here? If you have 2 inputs giving you the same output, what do we want to argue? We're trying to prove that G is 1 to 1. So this is how we begin. Take 2 inputs so that they have the same output. What is our job? To show that the inputs are the same, right? Same output implies same inputs. Now, why am I going this way instead of using the other approach? Well, because now we just put our formulas and we solve. Okay? So then, from here it follows that G of A is A over 2 plus 0.1, and that will be equal to G of B, which is B over 2 plus 0.1, and now it's just algebra. You subtract, cancel the 0.1, so you get A over 2 equals B over 2, multiplying by 2, both sides, give you that A equals B. Yes? Again, you have done tons of problems like this in the homework, right? If you already did the homework on this, there are many little exercises, which is this is what you do. Okay, so G is injective. Okay, so we just produce a one-to-one function from the open interval 0, 1 to the closed interval, and we also produce a one-to-one function from the closed interval to the open interval. So now that we found these 2 one-to-one functions, they were very easy to find, we can now call the theorem and say, because we have these 2 one-to-one functions, then we know there exists a bijection. I cannot give it to you, but I know it exists. Okay? So then, therefore, by the above theorem, there is a bijection between the open interval 0, 1 and the closed interval 0, 1. So that means that they have the same cardinality. Okay? So when we're talking about infinite sets, cardinality is no longer amount of elements. Okay? It's more about size. They have the same size. Because you can make a one-to-one correspondence between their elements. Okay? But for infinite cases, for infinite sets, size is not the same thing as amount of elements. Okay? We're going to dive more into this in the next section when we talk about cardinality. That's why we need to learn about functions first, because when you deal with infinite sets, we have to be talking about bijections, injections, and so on, and then you have to know. Okay, any questions? All right, so on Wednesday, I'm going to do more examples because I want to do at least one example proving that a function is onto and so on. Okay, and it could be some interesting exercises. Let me just give you something food for thought. So consider the following function f from c cross z to z, and what the function does is it takes a pair of numbers and then it sends it to the difference of their squares. And the question is this onto? So is f surjective? If you say yes, you have to prove it. If you say no, you need to give me a counterexample. Okay? In other words, we get all of you this way. All right, so on Wednesday, we do this, and then we have time, we begin cardinality. If not, then that will be for next week.